So in this section, we're going to start by introducing linear prediction, which is one type of prediction. We will start by introducing it with two variables, and then we'll move on in the next section into multiple variables. We're going to look at this in both math, and we're going to look at it in code. The module is also designed to show you how prediction relates to systems theory and how it relates to data science. So this slide introduces you to three different views of data science. One view is basically what I would call a data view or a table view. And the idea is that you've got data and it's in a table. So maybe you have the X and the Y data in a table. That X and Y could be anything. It could be the age and height of different people in the database. So anyway, you've got an X and a Y, and it's possible that you have other rows of data where you have some of this information, but maybe some values of Y are missing, and maybe even there's some cases where both are missing, and prediction would be used to fill in the data that is not available, the ones that you don't have, your best estimate or guess for what that would be. A second view of data science would be what I would call the math view, or in some ways like a graphical or model view of data. And in this case, all those values that were in the X and Y table, now they are points. They're somewhere on a graph or in a space. And the question is, if you have all of this data, is there some way, some model, some line, something that you could use so that if you knew one of these values, the X, you would have an estimate. That is, if you knew X and you knew the model, that you could predict back what should the Y value be. Okay, so that would be a math view. And then there's also a systems view. And in systems view, we think of values of X as being put into a system. We don't necessarily know what's on the inside, but we get values of Y on the outside. So we put in 2, we might get 3. And over time, we may have put in many inputs into the system, and we may have had many outputs from the system. And we use that to learn or to have a model, maybe a mathematical model like the one I just showed you, this linear one. And so if we were to put in a value that we've never seen before, an 8, into the system, then we could guess what might be the predicted value. And so these three views, the data view, the math view, the systems view, these are all to some degree interchangeable and different views of really the same thing. So one way to go about prediction is to just assume that all of the data that you have is in a line or is following a model that's a line. And if you do this, then what we need to do is guess which line best fits the data that we have. And what does it mean to best guess? Well, it means to pick a slope. So how much does it rise for any given run? What is the slope of this line? And we need one more point, and usually that point would be the y-intercept. So if you have the slope and you have the y-intercept, I'll call it c for a moment here, then you basically have a model for a line. And then, as I said before, you could take any value of x and use that to predict out what would be the ideal, what would be the likely value of y that comes from that. So the other thing that is going to come out here is, how do you know that this line is a good or bad estimate? How do you know that that's a good predictor? And usually the way that we do that is we figure out how much error do you get. So with every point that you can put in, particularly the new points, then there is an error. So if I take this point, there is an error. There's an error for every single point. The most common way to measure the error overall is to take all those differences and square them. And then you average that and you get basically what's called the mean squared error. So it's the squared value of all the errors averaged together. Okay, mean squared error. And this is usually what people use in order to estimate how good of a predictor this particular model is. Of course, the data that we have might or might not actually fit a line. In some cases, a line might be a perfectly good fit for the data that we have. In other cases, a line might not be the best fit for that data. And so we can, of course, choose models that are not lines or nonlinear models. The only thing is that sometimes when we choose models, we might get a model which fits really well, almost perfectly, with the data that we've shown it so far, but it might not fit so well for data that it hasn't seen yet. If we have that situation, then of course that's called overfit. And the basic trade-off is you might use a rough model, like a line, and that might work fine, or you might use a very complicated model that fits data in all kinds of very odd or unique ways, but then there's a chance that you've actually fit it too much and that it won't work when new data comes about. It won't work for predicting data that you haven't seen so far. Now, if we do want to use a line as a predictor, then this is how we would basically do it. First of all, we've got data from the table, and you can think of it as various points on this graph. And clearly, we're looking for a line that's going to be a good fit through all of this data. Now, the first thing that we're going to do, of course, is try to choose a y-intercept and a slope, some sort of slope for this line. Turns out that the best predictor has a slope, m, which is equal to the covariance of the xy divided by the variance of just the x variable by itself. Okay, now the other thing that makes the best linear predictor is that it runs through the very middle of all of this data. So if you have all the x values, like in the table, then you would know what is the average of all of those x values. And similarly, you would know what is the average of all the y values. If you just look at that one point, which is right in the middle of the x and y, and you have your line run through that point with a slope that has that ratio of covariance xy over variance of x, then you basically have this best linear predictor. Okay, so let's just think about it briefly. What happens, and I just want you to have some intuition about this, what happens if y actually equals x? And in this case, what you'll see is that the covariance of xy becomes the same thing as covariance of x comma x, and therefore your slope is going to be equal to the same as the variance of x over the variance of x. In other words, it's going to equal to 1. So your slope is going to be 1. And that makes perfect sense. If y is equal to x, then this covariance has a value of 1. So now what happens if we have another case, which is y equals 2x? Well, what will happen is that your covariance term is going to be covariance of x comma 2x divided, and then that's on top of, we're calculating the slope here, over the variance of x. But this top term is going to turn into 2 times the variance of x. You can just look at this formula and figure that out. And so what you're going to get is the value of 2. And that makes sense also. So if y was equal to 2x, your slope increased not from 1, but now to 2. And in general, the basic intuition that you should have here is that if you were to divide this space of all these points into the different quadrants, and I'm going to erase this so that we can do this again. So if you divide this into the quadrants, all the points that are here and all the points in this quadrant are going to give you positive values. So you see what's going on is that you're really taking the average of x minus its mean minus y minus its mean. So for any given point, let's say this one, it's got an x minus its mean, that's that distance, and y value minus the expected value of y, that's this distance. Both of those two are positive in this entire quadrant, and they're both negative in this entire quadrant, which means that the product is positive in both of these quadrants. And likewise, all the points here and here are negative. So if you have a lot of points in these two quadrants, then you're basically going to have a positive covariance. And if you have lots of points that are in this quadrant and this quadrant, so all your data was like this, you're going to see that you're going to have a negative covariance. Okay, and that's the term that's on the top. And the term that's on the bottom that determines your slope is the variance of x. Variance of x is always a positive number, but when variance of x is very small, then your slope is going to be higher. And when the variance is broad, when it's wide, then you're going to have a shallower slope. So anyway, that's the intuition for covariance. And that's how we pick the value of m, and it's how we pick the y-intercept. Now, here's a very practical example. Here's a table with values of x and y. And what we're going to do is we're just going to simply calculate what is the best linear predictor given this sample data. This is how we do it. So the data that I just showed you is right here. This is the x and the y column. And what you can see from this is you can maybe think of this like a spreadsheet. And what we can do is we can calculate the average of this column, and you'll see you get the expected value y. You can calculate the expected value of x here and the expected value of y here, the average of that column. We can also get values for the expected value of the product and just the expected value of x times x. So here and here. And so now our goal is to calculate covariance. Since we have all these numbers, we can just plug in the formula basically, and we'll get 21 minus 4 times 6.2. You can see where these numbers are coming from. And you get a slope of negative 3.8. And then the other thing that we're going to do is take those same values and put them into this formula, the value for the y-intercept, and we're going to get a value of 13.8. So on this graph here, if we picked a value that's approximately 13.8 and a slope which was equal to negative 3.8, then we're getting this line, which is our predictor, our best linear predictor for this data. And that means, of course, you could take any new value of data that you have, a value of 3, and find a point on that line and get back a predicted value of 8, for example, just as an example. Okay, now what I want to show you is that same thing, the same spreadsheet-based calculation, we'll do it in code. So we're going to do a code sample, and we're going to do it with NumPy. But one point is that people rarely write this code because library functions exist to do it. So this code that you're looking at here is just to illustrate. And in NumPy, we can do this. For example, X is the very same data that was in the table. Y is the same data that was in the table. We can calculate the expected value of XY just with the mean function or method. We can calculate the covariance from the defining formula. We can calculate the y-intercept and the slope simply with these lines. And we can therefore create a predictor. So you see, if you put in any value of X here, and these are now calculated variables, the y-intercept and the slope, we will get out a predicted value of Y. And in fact, in this code, what we're doing is we're taking all the data points that were put in and finding out how much error they had and squaring it. And so the output of this actually gives us the expected mean square error for this linear predictor. So in reality, we typically use library functions to do the same thing as the code that you just saw on the last slide, or the formulas and table-based approach that we did, spreadsheet-based approach that we did on the slide before that. And what you're going to see is, in this case, we're going to do it with the scikit-learn library. In fact, we can use this to introduce scikit-learn, which you're going to see again later on. But one reason for introducing it is that this is a very common machine learning library. So you're going to look at the same thing, but done with a machine learning library now. And you'll see how simple it is to do this. So in this case, we have two arrays of data, the X and the Y. I'm going to change the color here. The X and the Y are now in the variables X train and Y train, which means it's the values which we're going to use to train the library. First thing that we do is that we import the library. So from scikit-learn, import the linear model, this particular one, and then we instantiate it on this line. So model equals linear model, and specifically the linear regression model. And this next line is really where we train it. And we're going to use the value fit. Now, let's just think about what's going on. We have lots of data, and all these yellow points represent the values that are in X train and Y train. So that's all your data. And we're looking for the best line that fits through here. And all we need to do that is to know, again, what is the best slope, what is the slope of that best line, and we want to know what is the y-intercept, and I'll just call it C for now, that intercept. So in the last equations, we showed you how we calculate that. In this case, that's hidden from you, and all you have to do is use this model.fit, the fit method. You put in the values of X and Y, and it will go and do some calculation. And when it comes back, what will happen is that the fit method has basically calculated these two values for you. And when it calculates those values, it has basically learned from all of these data points that you put in. And then if you would like to do predictions, you can put in values of X and get predicted values out. You can get the whole array of predicted values out. You can even put in data, in this case, the test data that the model has never seen, and you can get values of Y that are predictions for those things that it's never seen. And of course, you can compare the predicted values with the actual ones that you happen to know in your test set, and you'll be able to get an estimate for the error. So this is the end of this section of the module. What we're showing here is that we looked at linear prediction for 2 variables. We looked at it in math. We looked at it in code, NumPy, and then we even looked at it in a machine learning library, Scikit-learn. In the next module, we're going to see how the same system works, but for the case of more than 2 variables.